Hey guys, welcome to Trig 11 on the sum and difference identities. Now, in this section today, we're going to be using formulas that involve sum and differences to help us verify identities. So what I'm going to do, I'm going to bring you through all 6 of the formulas. I'm going to explain them as I go. And more importantly, I want to talk about why it is that we're actually using these formulas, okay? So make sure you follow along closely as I explain. We're going to start on the left-hand side of the table. Let's go ahead and look at the sine, cosine, and tangent of the sum of angles. So we're going to start with the sine of alpha plus beta. Now what this is saying is if I am taking the sine of 2 angle measures added together, such as the sine of alpha plus beta, I can break that down into the following formula. We can take the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta, and that is going to give us the measure of sine of alpha plus beta. Now, moving down, the cosine of alpha plus beta looks a little bit different. So if we're taking the cosine of 2 angles added together, the cosine of alpha plus beta, that breaks down into the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. Now, last but not least, let's say I want to take the tangent of 2 angles added together. So if I have the tangent of alpha plus beta, that breaks down into the tangent of alpha plus the tangent of beta over 1 minus the tangent of alpha times the tangent of beta. Now, why might these formulas be useful? Well, let's think about it this way. What if I were to ask you what the sine of 7 pi over 12 was? And you might think to yourself, well, 7 pi over 12 does not lie on the unit circle. It's not one of those special angles that I know. So how would I go about evaluating what this sine is equal to? Well, let's think about it this way. 7 pi over 12 is the same thing as pi over 3 plus pi over 4. And I know how to evaluate the trig functions at these 2 angles, pi over 3 and pi over 4. So if I were to rewrite a more complicated angle measure as the sum of 2 special angles, then I could easily calculate what the sine of 7 pi over 12 is equal to. All I have to recognize is that the sine of 7 pi over 12 is the same thing as taking the sine of pi over 3 plus pi over 4. And then I can plug in pi over 3 for alpha and pi over 4 for beta. And since I can evaluate all of the trig functions at these special angles, I will easily find the answer to the sine of 7 pi over 12. So essentially, the sum and difference identities exist to help us evaluate more complicated angle trig measures, okay? Now let's talk about the difference identities. So we can also do the same thing for the difference of 2 angle measures. Let's go ahead and start with the sine of alpha minus beta. That's going to break up into the sine of alpha times the cosine of beta minus the cosine of alpha sine of beta. So notice how it's the same formula as the sum identity. The only difference is the sign in the middle changed to a negative. Moving down, if we have the cosine of alpha minus beta, that breaks into cosine of alpha cosine of beta plus sine of alpha sine of beta. Once again, same formula as the sum. The only difference is the middle sign is now a plus sign instead of a minus sign. Last but not least, the tangent of alpha minus beta is equal to the tangent of alpha minus the tangent of beta over 1 plus the tangent of alpha tangent of beta. Again, same exact formula as the sum. The only difference is we change the signs in the numerator and the denominator. So those are the 6 sum and difference identities. Now, why might the difference identities be useful? Well, once again, let's say we're taking the sine of, this time, let's say we're taking the sine of pi over 12. I know that pi over 12 can be written as the sine of pi over 3 minus pi over 4. And since I know how to evaluate trig at these 2 special angles, I could easily plug in these angles for alpha and for beta, all right? So once again, it is useful to help us simplify expressions. Now, what are some ways that we can memorize these formulas? Because obviously there's a lot going on here, especially with signs. So here are a couple of tips we can use to help us memorize the formulas. First of all, I want you to recognize that the sign keeps the operation when expanded. Okay, so the first thing we're going to write down is the sign keeps the operation when it's expanded. And what this means is, if we're taking the sine of alpha plus beta, then we are breaking this down into the sine of alpha cosine of beta plus the cosine of alpha sine of beta. Notice how the sign stayed the same, all right, or the operation, the plus sign here, it remained the same even when we expanded it. So what you need to remember is that sine keeps the operation when we expand it. Now, on the other hand, cosine changes the operation. Okay, so I'm going to say cosine changes signs. So if we take a look at the cosine formula up here, if I have the cosine of alpha plus beta, we break it into the cosine of alpha cosine of beta minus the sine of alpha sine of beta. So if I'm taking the cosine of a sum, when I expand that formula, the sign changes to a minus sign, all right? So sine keeps the operation, but cosine changes the operation. Now, another tip to help you remember these formulas is that sine and cosine, or excuse me, let's just talk about sine at first. So sine alternates between sine and cosine. All right, so if we look at the sine formulas up above, notice how they alternate. So when I'm taking the sum of two angle measures, the sine of that is going to be sine of alpha cosine of beta plus cosine of alpha sine of beta. So notice how we just alternate sine and cosine, all right? On the other hand, so I'm going to say, but cosine, on the other hand, is grouped as follows. Cosine is grouped as cosine with cosine and sine with sine. Okay, so when we're expanding the cosine, either addition of two angle measures or subtraction between two angle measures, when I'm expanding the cosine of the sum or difference of two angles, we group the terms as cosine, cosine, and sine, sine. So those are just a couple of characteristics to remember and things to help you memorize what the sine looks like and what the cosine looks like. Now, when it comes to tangent, you just got to remember the tangent formula, a little bit more complicated, and especially also because we have several different signs happening. So obviously, if I have the sum of two angle measures and I'm taking the tangent of that, the numerator is just going to be tangent of alpha plus tangent of beta, but the denominator is 1 minus the tangent of alpha, tangent of beta. So just remember, if I'm taking the sum of two angle measures, when I expand the tangent, the same operation is going to remain in the numerator, but then the opposite operation happens in the denominator. And then obviously, when I'm looking at the difference identity for the tangent, it's just the complete opposite. So obviously, the numerator here is going to keep the negative, but the denominator is going to turn into a positive. So we just got to alternate the signs with the numerator and denominator for the tangent identities. All right, but those are just some tips to help you remember these formulas. All right, so let's go ahead and move down, and we are going to apply the 6 formulas that I just taught you. Example number 1, find the exact value of the cosine of 70 degrees times the cosine of 40 degrees plus the sine of 70 degrees times the sine of 40 degrees. The first thing we should probably do here is we should figure out which formula this setup corresponds to. We have cosine cosine plus sine sine. And looking up above here, the only formula that has cosine cosine plus sine sine is this one right here, the cosine of alpha minus beta. So if I look a little bit more closely at this setup, since my first angle measure in question is 70 degrees, I can say that alpha is 70 degrees, and the second angle measure in question is 40 degrees, so I can say beta equals 40 degrees. Now, like I said before, the formula that this setup aligns to is the cosine of alpha minus beta. So I could rewrite this as the cosine of alpha, 70 degrees, minus beta, 40 degrees. Now, if I were to simplify the inside of these parentheses, 70 minus 40 is going to give me the cosine of 30 degrees, right? And I know what the cosine of 30 degrees is because that's one of those special angles on the unit circle. Keep in mind that 30 degrees is the same thing as pi over 6, all right? They are equivalent to one another. So if I were to look at the unit circle, when that central angle is 30 degrees or pi over 6, all right, so I'm going to say this angle right here is 30 degrees. We know that on the unit circle, the x value of that point of intersection would be root 3 over 2, and the y value of that point of intersection would be 1 over 2. So the cosine is the x value on the unit circle, which in this case is root 3 over 2. So the cosine of 30 degrees is root 3 over 2, and this is the final answer for example number 1. So as you can see, the goal is to simplify trigonometric expressions using the sum and difference identities. All right, let's go ahead and move down to example number 2. So we're going to write the following expressions as the sine or the cosine of an angle. Well, let's go ahead and look at example A. We have the sine of 22 degrees, cosine of 13 degrees, plus the cosine of 22 degrees times the sine of 13 degrees. So what we need to do is we need to look up above and see which formula has sine cosine plus cosine sine. If I look up here, the only formula that has sine cosine plus cosine sine is the sine of alpha plus beta. So in this case, I know my first angle is 22 degrees, so alpha is 22 degrees, and the second angle we're looking at is 13 degrees, so beta equals 13 degrees. And like we said, this setup aligns to the sine of alpha plus beta, so we're really looking at the sine of 22 degrees plus 13 degrees. Now, if I were to simplify the inside of the parentheses here, 22 plus 13 is going to give me the sine of 35 degrees, all right? So this is written in terms of sine or cosine, and this is my final answer. All right, at part B, we have cosine of pi over 3 times cosine of pi over 4 plus sine of pi over 3 times sine of pi over 4. The only setup from up above that has cosine cosine plus sine sine is the cosine of alpha minus beta. So we know that alpha is pi over 3. That's my first angle in question. Beta is equal to pi over 4. So if I know that those are the two angles that we're using here, we're just going to plug that into the cosine of alpha minus beta. So I'm going to have the cosine of pi over 3 minus pi over 4. All right. And if we were to simplify this, obviously we need like denominators. So we have a 3 and a 4. The common denominator here that I want to use is probably 12, since 3 and 4 both go into 12. So we're going to multiply the top and the bottom of this first fraction by 4. Therefore, we have the cosine of 4 pi over 12. And then for my second fraction, I want to turn this denominator into 12. So multiply the top and the bottom by 3. So we're going to subtract 3 pi over 12. I know that 4 pi over 12 minus 3 pi over 12 is going to give me 1 pi over 12. So we are actually finding the cosine of 1 pi over 12. And the question did not ask us to solve all the way. So this is just going to be my final answer. All right, let's go ahead and move on to the next page, and we're going to talk about some more ways to use these identities. Example number 3. So to find the exact value for the cosine of 15 degrees, this is what we are evaluating here. We are trying to find the cosine of 15 degrees, and we are going to use the fact that cosine of 15 degrees is the same thing as the cosine of 45 degrees minus 30 degrees. So we're going to use the difference formula for cosines to evaluate what the cosine of 15 degrees is equal to. And again, this is a prime example of why the sum and difference identities are important. We don't know how to evaluate cosine of 15 degrees in our heads because it's not one of the special angle measures, but I do know that this can break up into the difference of two special angle measures, all right? So let's go ahead and say, well, if this is 45 minus 30, we're going to say that alpha is 45 degrees and beta is 30 degrees. And now we just got to figure out what the formula is for the difference identity of cosines. So if I have the cosine of one angle minus another, that's going to be this formula right here. Cosine of alpha minus beta equals cosine of alpha, cosine of beta, plus sine of alpha, sine of beta. Remember when it comes to cosine that we change the sign when we expand the operation and we group cosine as cosine, cosine, sine, sine. All right? So let's go ahead and break it up into the formula. The cosine of 45 degrees minus 30 degrees is equal to cosine, cosine plus sine, sine. So we have the cosine of 45 degrees times the cosine of 30 degrees plus the sine of 45 degrees times the sine of 30 degrees. All right. So in order to solve this, what we're going to have to know is that on the unit circle, we have to know that if we have a 30-degree angle, or in other words, if we have pi over 6 as our central angle, then our point of intersection is going to be root 3 over 2, comma 1 over 2. And we know that the cosine corresponds to the x value, the sine corresponds to the y value. So if we're evaluating the cosine, for example, of 30 degrees, that's going to be root 3 over 2, whereas the sine is 1 over 2. Now we also need to know what's happening with 45-degree angles. So let's say we have a 45-degree angle here. Keep in mind that the point of intersection on the unit circle for the angle measure 45 degrees, or in other words, pi over 4, that point of intersection is root 2 over 2, comma root 2 over 2. So the cosine of 45 degrees as well as the sine are both going to be root 2 over 2. So we're going to use those bits of information to evaluate the individual trig functions in this formula. So we have the cosine of 45 degrees, that's going to be root 2 over 2, multiplied by the cosine of 30 degrees, which we know is root 3 over 2. And then we're going to be adding to that the sine of 45 degrees, which is root 2 over 2, multiplied by the sine of 30 degrees, which we know is 1 over 2. So now, to solve the problem, we have just got to simplify both sides of this expression. So starting off, we have root 2 times root 3 all over 2. So that's going to be, or excuse me, we have root 2 times root 3. That's going to give me the square root of 6, all right? Because we know with radicals, we can just multiply the insides of the radical together. And then 2 times 2 for my denominator is going to give me 4. Now for my second side of the expression here, we have root 2 times 1 in the numerator. That's going to give me root 2. And then 2 times 2 in the denominator, that's going to give me 4. So my final answer, since I have like denominators here, is just going to be root 6 plus root 2 in the numerator, all over that common denominator, 4. And that's my final answer. All right? Okay, so let's go ahead and change gears a little bit. We're going to move down to example 4. And what I want to stress to you is that these identities are not just useful for identifying the trig values of non-special angles. They're also useful for verifying identities or completing proofs, right? Now we have added 6 new formulas to our bag of tricks that we can absolutely pull out anytime we are trying to prove a trigonometric identity, right? So I want you to keep in mind all 6 of these formulas and how we can integrate those into proofs to help us get one side of the equal sign to equal the other. So if we look at example number 4, we have to verify the identity, and we have the cosine of alpha minus beta over the cosine of alpha times the cosine of beta, and we have to prove that that is equal to 1 plus the tangent of alpha times the tangent of beta. Now, whenever we're completing proofs, a couple of things you guys need to keep in mind. First of all, we only want to work on one side of the equal sign. We absolutely cannot make operations and changes to both sides. We have to stick to one side, and we have to stick with it the entire time. Also, we probably want to change the side that has the most going on. So whatever the more complicated side is, that is the one that we want to mess around with. So if we look at example number 4, this first side of the equal sign is probably the more complicated of the two. All right, so I'm going to focus more on this left-hand side of the equal sign. Now, also, we want to think about what we can replace before we get into it. Notice how the numerator of this fraction is the cosine of alpha minus beta. And we absolutely do have an identity that we could replace the cosine of alpha minus beta with. We just need to refer to the formulas on the previous page. Now, keep in mind, whenever we're rewriting the cosine of alpha minus beta, to expand that, we're just going to change the operation. So instead of minus, we're going to have plus. And also, whenever we deal with expanding cosine, we break it up into cosine times cosine and sine times sine. So the cosine of alpha minus beta can be rewritten as the cosine of alpha times the cosine of beta plus the sine of alpha times the sine of beta. And that is all over the cosine of alpha times the cosine of beta. And again, we are proving that that equals the right-hand side of the equation. Now let's think about how else we can modify this expression. Well, I have two terms in my numerator. I have cosine of alpha times cosine of beta and sine of alpha times sine of beta. But I only have one term in my denominator. So if I wanted to split these fractions into two, I absolutely could. I would just set each term in the numerator individually over the shared denominator. And if I were to do that, notice how the first fraction would be the cosine of alpha times the cosine of beta over the denominator, cosine of alpha times cosine of beta. So obviously we would have a huge amount of cancellation here. Now my second fraction, if I were to break this up, would be plus the sine of alpha times the sine of beta over the denominator, cosine of alpha times cosine of beta. Now, if I were to split those apart, the first fraction, cosine of alpha cancels with cosine of alpha, then cosine of beta cancels with cosine of beta. That whole thing turns into 1. And for my second fraction, sine of alpha times sine of beta over cosine of alpha times cosine of beta, I can break that up into two separate fractions, right? Because we just have multiplication in the numerator and multiplication in the denominator. So that can break up into the sine of alpha over the cosine of alpha multiplied by the sine of beta over the cosine of beta. Now, we know, using the quotient identities that we learned a few lessons back, that sine over cosine is the same thing as tangent. So if we have the sine of alpha over the cosine of alpha, that can be written as 1 plus the tangent of alpha. And then the sine of beta over the cosine of beta, that is equal to the tangent of beta. So now we have found that both sides of the equal sign are equal to each other. So we found that the left-hand side is now equal to the right-hand side, 1 plus the tangent of alpha times the tangent of beta. And so we proved this identity. We are going to finish the process by writing QED. And now we are done. Next up, we have example number 5. So now we have to prove that the sine of pi over 2 minus x is equal to the cosine of x. As always, whenever we're proving something, we have to choose one side of the equation to work on and one side only. And we should probably choose the side that looks more complicated. So for example number 5, I am going to choose the sine of pi over 2 minus x to work on because that looks more complicated. Now, obviously, we have a difference identity for sine here. And whenever I expand the sine difference identities, keep in mind that the operation is going to be the same, and we are going to alternate sine and cosine. So the sine of pi over 2 minus x can be written as the sine of pi over 2 times the cosine of x. And again, we're going to keep the same operation minus, and then we're just going to alternate sine and cosine. So for the second term, we have the cosine of pi over 2 multiplied by the sine of x, all right? And we have to, again, prove that this is equal to the cosine of x. Now, since I have the sine and the cosine of an actual angle measure, let's just recall where this is located on the unit circle. On the unit circle, pi over 2 is right up here on the positive the positive y-axis. And so that point of intersection is going to be the point 0, 1. So the sine of pi over 2 is going to be 1. The cosine of pi over 2 is going to be 0. So let's make those appropriate substitutions. The sine of pi over 2, like we said, that's going to be 1. So we have 1 times the cosine of x on the left. And then we have the cosine of pi over 2, which is 0, multiplied by sine of x. Well, let's take a look at what happens here. 1 times the cosine of x is just the cosine of x. And then 0 times anything is just going to be 0. So we have proven that the cosine of x is equal to the cosine of x. So now that I have made that proof, I'm going to finish off by saying QED. All right, and that is how we prove example number 5. Let's move on to the next page and look at some more. Example number 6. So now we are going to find the exact value of the sine of 5 pi over 12 using the fact that 5 pi over 12 is the same thing as pi over 6 plus pi over 4. So now, instead of thinking of this as the sine of 5 pi over 12, we're going to think of this as the sine of pi over 6 plus pi over 4. All right, and those are both special angles that we know how to evaluate trig functions at. So what we know about the expansion of sine is that whenever we expand sine, we're going to keep the operation and we're going to group the terms as sine with cosine, and then we just alternate cosine and sine. And again, we are keeping the operation of addition. So if I break this apart, this is going to expand into the sine of pi over 6 times the cosine of pi over 4, keep the same operation, addition, and then we're going to alternate the trig functions. So for the second term, we have the cosine of pi over 6 multiplied by the sine of pi over 4. So now, in order to simplify this, we just have to evaluate the trig functions at the angles pi over 6 and pi over 4. So let's sketch these and their location on the unit circle, just so we have an idea. Pi over 6, that's going to have a point of intersection with the unit circle at the point root 3 over 2, comma 1 over 2. So we know the cosine is root 3 over 2, the sine is 1 over 2. Then for pi over 4, a little bit different. All right, for pi over 4, we have a point of intersection at root 2 over 2, comma root 2 over 2. So again, we know that cosine is going to be root 2 over 2, and so is the sine. So using these two locations and the points of intersection on the unit circle, let's make the appropriate replacements. So looking at sine of pi over 6, that's going to be the y value of the point of intersection with pi over 6, which is 1 over 2. So I'm going to say 1 over 2 multiplied by the cosine of pi over 4, which we know is root 2 over 2. Then I'm going to add this to the cosine of pi over 6, which is root 3 over 2, the x value of that point of intersection. And then we're going to multiply that by the sine of pi over 4, which again is root 2 over 2. So now let's go ahead and simplify by multiplying those fractions together. Looking at that first fraction, 1 plus root 2 is going to give me numerator of root 2, and then 2 times 2 gives me a denominator of 4. The second fraction, we have root 3 times root 2. That's going to give me root 6 in the numerator, all over 2 times 2, which is 4. We have like denominators here, so we can just add those numerators together. We get root 2 plus root 6 all over 4, and that is my final answer. All right, moving down to example number 7. Now we have find the exact value of the cosine of 7 pi over 12 using the fact that 7 pi over 12 equals pi over 4 plus pi over 3. So let's go ahead and think of this cosine now as cosine of pi over 4 plus pi over 3. Using the expansion formula for cosine, we know that we change the operation, so that's going to be minus. And also, we are going to group cosine as cosine with cosine and sine with sine. So this is going to break down into the expansion of cosine pi over 4 multiplied by cosine of pi over 3, change the operation to minus, and then we have the sine of pi over 4 multiplied by the sine of pi over 3. All right, so let's go ahead and sketch those off to the side here. We already have pi over 4 from above, but let's go ahead and sketch pi over 3. So pi over 3, if that is my central angle, we have a point of intersection with the unit circle at 1 over 2, comma, root 3 over 2. So let's go ahead and use that information to evaluate the following. We have the cosine of pi over 4, that's going to give me root 2 over 2. Then the cosine of pi over 3, that's going to be this x value, which is 1 over 2. And then I have the sine of pi over 4, that's going to be minus root 2 over 2, times the sine of pi over 3, which is the y value of this point, root 3 over 2. So just like we did before, let's simplify this a little bit. We're going to multiply these fractions together. So root 2 times 1 is going to give me root 2 in the numerator. 2 times 2 gives me 4 in the denominator. And then I'm subtracting root 2 times root 3. That's going to be square root of 6 all over 2 times 2, which is 4. Since I have like denominators, we're going to write that as one single fraction. We have root 2 minus 6 in the numerator and 4 in the denominator. And that is my final answer. All right, so let's go ahead and move down to the next example, which looks a little bit different. And we're going to go from here. So let's suppose that we have some angles alpha and beta, and here's the information we know. We know that the sine of alpha is equal to 4 over 5 for a quadrant 2 angle alpha. We also know that the sine of beta is equal to 1 over 2 for a quadrant 1 angle beta. And we're going to use this information to find the exact values of each of the following. Now, this is a lot of information that's given to us. So we're going to use this coordinate plane over here to sketch the information that's given just so we can keep everything straight. So let's start with the angle alpha. We know that the angle alpha has a sine of 4 over 5 and it lies in quadrant 2. So what I could do is I could draw this angle in the form of a triangle because again, I know what its sine is and I know that it lies in quadrant 2. So let's draw a triangle out of this angle. And I know that my central angle is some angle alpha. And if I know what the sine of this angle is, well, keep in mind that sine is opposite over hypotenuse. So if we have the fraction 4 over 5, I know that the opposite side of angle alpha must be 4, and the hypotenuse must be 5. So looking at alpha, the opposite side we can say is 4, and the hypotenuse we can say is 5. Now, if I wanted to finish off this triangle by finding the missing side, I could do one of two things. I could either use Pythagorean theorem and set up a squared plus b squared equals c squared, or I could recognize that this is one of those special triangles. This is a 3, 4, 5 triangle. And we know that because 3 squared plus 4 squared is going to give us 5 squared. So this bottom side of the triangle here is 3. Now, this is where we need to be careful. We are lying in quadrant 2, and in quadrant 2, the x values are negative and the y values are positive. So since this side of the triangle lies in the negative x-axis, the bottom side of that triangle is actually going to be negative 3 instead of positive 3. So just don't forget the rules of the signs in each of the quadrants. So that's what we know about alpha. Let's talk about what we know about beta. So the sine of beta is 1 over 2, and we know that beta is in quadrant number 1. So let's do the same thing we did before. We're going to draw the triangle that has the sine of beta equals 1 over 2. Okay, so that's going to look something like this. Again, we have a central angle beta, and we know that the sine, or the opposite over hypotenuse for the beta angle, is going to be 1 over 2. So opposite of beta must be the numerator 1, and the hypotenuse of beta must be 2. So now I'm going to use that information to fill in the missing side here. Now for this one, I should probably use Pythagorean theorem. So let's set up a squared plus b squared equals c squared. I'm going to call this missing side length x here. So we're going to call this a squared plus b squared, which is x squared plus 1 squared. And that has to equal the hypotenuse squared, 2 squared. If I simplify this, I get x squared plus 1 equals 2 squared, which is 4. Subtract 1 from both sides, we get x squared equals 3. Take the square root of both sides, we get x equals the square root of 3. So the bottom of this triangle is going to be the square root of 3. And we know in quadrant 1, both x's and y's are positive. So that is appropriate to be the square root of 3. Now, using this information, we're just going to follow along with SOHCAHTOA to figure out what these trigonometric values are equal to. So let's go ahead and start with part A, the cosine of alpha. Well, if I look at alpha, I know that cosine is adjacent over hypotenuse, so the cosine of alpha is going to be the adjacent side negative 3 over the hypotenuse 5. So we just get negative 3 over 5. That simple. Now part B, we have the cosine of beta. Looking at angle beta, cosine is adjacent over hypotenuse, so adjacent is square root of 3, hypotenuse is 2, so the cosine of beta is the square root of 3 over 2. All right, moving down to part C, a little bit more involved, we have the cosine of alpha plus beta. Well, keep in mind here that the cosine of alpha plus beta can be expanded into the opposite operation minus, and then we group it as cosine, cosine, and sine, sine. So let's go ahead and break this apart. This can be written as the cosine of alpha times the cosine of beta, opposite operation, so we're going to turn this to subtraction, and then we have the sine of alpha times the sine of beta. All right, so let's fill in the missing information here. We have the cosine of alpha, which we know is negative 3 over 5. So let's make that substitution, negative 3 over 5, times the cosine of beta. I know the cosine of beta is root 3 over 2. And we are subtracting the sine of alpha times the sine of beta. Well, the sine of alpha, that is going to be right up here, 4 over 5, multiplied by the sine of beta, which we know is 1 over 2. So now we just got to simplify. Looking at my first fraction here, we have negative 3 times the square root of 3 over 5 times 2. That's going to be negative 3 square root 3 over 10 minus 4 times 1 over 5 times 2, which is going to be 4 over 10. If I write those as one single fraction, since I have like denominators here, that is going to give me a final answer of negative 3 square root of 3 minus 4 all over the common denominator, 10. All right, so that's my final answer for part C. Now for part D, we have something similar, the sine of alpha plus beta. So we just have to use that expansion formula. So if we're taking the sine of alpha plus beta, keep in mind for sine, we're going to keep the operation and we're going to group this as sine, cosine, and then alternate cosine, sine. So let's go ahead and expand this. We have the sine of alpha times the cosine of beta. And again, we're going to keep the same sign, addition, and then we're going to alternate cosine of alpha times sine of beta. All right, so let's fill in what we have. The sine of alpha, as given above, is 4 over 5. So we're going to replace that with 4 over 5. The cosine of beta is what we found up here, root 3 over 2. All right, then if I look at cosine of alpha, the cosine of alpha is equal to negative 3 over 5. So make that substitution over here, multiplied by the sine of beta, which I know from above is 1 over 2. All right, so let's go ahead and simplify what we have here. Obviously, we have some multiplication that we need to deal with using the order of operations. So looking at my first fraction, I have 4 times the square root of 3 in the numerator. So that gives me 4 root 3 over 5 times 2, which is 10. Looking at my second multiplication situation here, we have negative 3 times 1 on the top. That is just negative 3 over 5 times 2 on the bottom, which is 10. I do have like denominators, so I can combine these fractions. My numerator is going to be 4 root 3 minus 3, and my denominator is just going to be 10. So that is my final answer. All right, you guys, let's go ahead and move on to the next page, the last page of the notes, And we'll go over just a couple more examples. All right, so let's talk a little bit about what's called reduction formulas. So if one of the angles in a sum or difference is a quadrantal angle, then the sum or difference identity yields a single-termed expression. Now, since the result is less complicated than the resulting identity, it is called a reduction formula. All right, so let's go ahead and look below at example number 9. We have 2 reduction formulas listed, and what we have to do is we have to take each of these and prove them. So let's start with the sine of x plus pi equals negative sine of x. So I'm going to work with one side. Let's work with the left-hand side because that looks more involved. And looking at that left-hand side, I can absolutely expand that using the sum and difference identities. For sine, we know that we keep the operation and we alternate sine and cosine. So that can be expanded to sine of x times cosine of pi plus cosine of x times sine of pi. Now, I'm going to substitute what the cosine of pi and the sine of pi are equal to because I know using the unit circle, I can evaluate those no problem. Now, since pi is on the negative x-axis and it has a point of intersection at -1, 0, I know that the cosine of pi is -1 and the sine of pi is 0. So let's make those substitutions. We have the sine of x multiplied by the cosine of pi, which we said was -1, plus the cosine of x times the sine of pi, which is 0. All right? So since I have the cosine of x times 0, that's just going to cancel and turn into 0, and we are just left with sine of x times -1, giving us negative sine of x equals the right-hand side, negative sine of x. Whenever I prove something, I always want to finish off by saying Q, E, D. All right. Now let's prove the second one. So now we're going to look at the cosine of x plus 3 pi over 2, and we have to prove that that is equal to sine of x. Well, once again, let's use that expansion formula for the sum identity of cosine. So we're going to have to change the operation here and group cosine with cosine and sine with sine. So we have the cosine of x multiplied by the cosine of 3 pi over 2. And we're going to change the operation, so we have subtraction. And then we have the sine of x multiplied by the sine of 3 pi over 2. And again, we are proving that that is equal to the positive sine of x. Now, if I'm talking about 3 pi over 2 on the unit circle, 3 pi over 2 is the negative y-axis, which has the point of intersection 0, -1. So cosine is going to be 0, sine is going to be -1. So let's make those substitutions and simplify. We have the cosine of x, but I know that based on the unit circle, the cosine of 3 pi over 2 is 0. So we have the sine of x, or excuse me, the cosine of x multiplied by 0. Now for the second side, we have minus sine x times the sine of 3 pi over 2, which we know is -1. So I have sine of x multiplied by -1. Now to simplify this, obviously anything times 0 is going to turn into 0. And then negative sine of x times -1, that's going to give me positive sine of x. So I found that sine of x equals sine of x. Again, whenever I prove something, I finish by saying Q, E, D. All right? So that is just the way that we prove the reduction formulas. Again, we proved that both sine of x plus pi and cosine of x plus 3 pi over 2 equals the right-hand side of the equal sign. All right, we have one final example for today's lesson, and we're going to talk about tangent because we haven't discussed the tangent formula yet. So example number 10, we're going to find the exact value of the tangent of 5 pi over 12 if alpha is 2 pi over 3 and beta is pi over 4. Well, first of all, obviously, we have to figure out, well, is this going to be addition or subtraction to give us 5 pi over 12? Well, obviously, since we have essentially 2/3 and 1 over 4 as the two fractions I'm looking at here, if I were to take 2/3 plus 1 over 4, that would give me well above 1. And I can see that 5 over 12 is obviously less than 1. So we must be taking alpha and subtracting beta because 2 pi over 3 minus pi over 4 would give me 5 pi over 12, all right? So what we're looking at here is the tangent of 2 pi over 3 minus pi over 4. All right, so let's go ahead and use the tangent formula here. Well, if I look back at the first page, because I haven't used this one yet, so I haven't memorized it, but looking at the tangent formula for the difference, we are going to be looking at tangent of alpha, let me write this down for you, minus tangent of beta, all over 1 plus the tangent of alpha times the tangent of beta. So again, when it comes to the tangent formula, we're going to keep the operation for the numerator, and we just take the tangent of both angles. Then for the denominator, we change the operation, and we are taking 1 plus the tangent of both of those angles multiplied together, all right? So if I translate this to the problem that I have, this is going to be the tangent of alpha, or 2 pi over 3, minus the tangent of beta, tangent of pi over 4 right here, all over 1 plus the tangent of alpha, which is 2 pi over 3, times the tangent of beta, or in our case, the tangent of pi over 4. So obviously, to simplify this, we need to know a couple things. First of all, we need to know what the tangent is at 2 pi over 3, and we also need to know what it is at pi over 4. Well, 2 pi over 3 on the unit circle lies right about here, a little bit to the left of that positive y-axis. This has the point of intersection, negative 1/2, comma, root 3 over 2. And again, that is for the angle measure, 2 pi over 3. So if I were to take the tangent of this angle measure, I have to divide sine divided by cosine. So if I take sine divided by cosine, I have root 3 over 2 multiplied by the reciprocal, which would be negative 2. And since I have a 2 in the denominator and a 2 in the numerator, this would turn into negative 1 times the square root of 3, or negative square root of 3. So we found that the tangent of 2 pi over 3 gives me negative square root of 3. All right? So let's go ahead and make the substitution. So I have negative square root of 3 for the tangent of 2 pi over 3 minus the tangent of pi over 4. Well, pi over 4 on the unit circle has the point of intersection, root 2 over 2, root 2 over 2. Right? And that's for pi over 4. So if I were to take the tangent of this, well, the sine divided by the cosine is just going to turn into 1. So we have negative square root of 3 minus 1 all over 1 plus the tangent of 2 pi over 3. Again, we said the tangent of 2 pi over 3 is negative square root of 3. So I have 1 minus the square root of 3 multiplied by the tangent of pi over 4, which is just 1. Obviously, if I simplify this, I get negative square root of 3 minus 1 all over 1 minus the square root of 3. Now, I don't like any radicals in my denominator. So what we have to do is we have to rationalize the denominator here before we call it a day. Now, to rationalize a denominator, when we have an actual operation happening here, like 1 minus the square root of 3, we have to multiply it by its conjugate. So instead of multiplying this by just the square root of 3, we're going to have to multiply by 1 plus the square root of 3. Right? You might recall this from one of our previous units when we had to rationalize the denominator. Whenever we have a binomial happening, we have to use the conjugate to rationalize. So now I'm going to have to FOIL the numerators because I have binomial multiplied by binomial. So first, outer, inner, last here. First is going to be negative square root of 3 times 1, which is just negative root 3. Outer is negative root 3 times positive root 3. Negative times positive is negative, so that's just going to give me negative 3. Inner, we have negative 1 times positive 1, which is just negative 1. And last is negative 1 times positive square root of 3, which is just negative square root of 3. The denominator, if I multiply those, I have to FOIL yet again. So first is 1 times 1, or 1. Outer is 1 times positive root 3. Now, if we were to do inner, inner is negative root 3 times 1. So positive root 3 plus negative root 3 is just going to turn into 0. And then last is negative root 3 times positive root 3, which is just negative 3. Okay, so let's simplify this a little bit more. If I simplify this farther, I have negative root 3 minus root 3. That's going to give me negative 2 root 3. And negative 3 minus 1 is negative 4. So we have negative 4 minus 2 square root of 3 all over my denominator 1 minus 3, which is negative 2. Now notice how these three numbers that form this little triangle here, right? Apparently I can't draw a triangle, but those three numbers are all divisible by 2. So if I divide all of those by 2, I'm going to get negative 4 divided by 2 is negative 2. Negative 2 divided by 2 is negative 1. So I just have negative 1 square root of 3 all over negative 2. But if that simplifies, divide that by 2, that's going to give me negative 1. Now, obviously, I don't just want to write a negative 1 in my denominator. So my final answer is just both of these terms divided by negative 1. Negative 2 divided by negative 1 is positive 2. Negative root 3 divided by negative 1 is positive root 3. So that is my final answer. All right, guys, and that is how we use the sum and difference identities of sine, cosine, and tangent to solve problems. Thanks for tuning in, and I will see you all next time. Have a great rest of your day.